Saxon Algebra 2, Lesson 85. Welcome to week 10, my students. This is going to be our 10th week of new lessons since the beginning of the year. That's a lot. And if you're tired and cranky by now, I understand that. Of course, I could do this endlessly. I never get tired and cranky of math, but I understand that you are in a different place than me, and P.S., I don't have to do the homework. But anyway, here we are, another week. We have 2 more weeks after this one. So we'll have 12 weeks before the midterm. So we're getting close to that. I know that there's a big project coming up at Westgate this week. I know that everyone involved in the culinary class, the Friday culinary class, and even some who aren't even in it this quarter, aka Kyle, I've renamed Clee, because I can't spell Kyle. That's too big of a word for me. But anyway, I know that you have a big conference you're preparing meals for, right? On Thursday and Friday, I know that you're going to be tied up in the kitchen all day. Let me just say this. I still need to talk to you this week. I am going to be very flexible and here for you, but I cannot be okay with us just skipping a week. We've had so many interruptions and crazy things happen. I really count on talking to you once a week to making sure you're on track, and especially at this time of year, I don't want anyone to wobble. So please find some time to touch base with me on Thursday or Friday. If that's absolutely unacceptable, we'll do it in the evenings, we'll do it on Wednesday, we'll do it on Saturday. We'll find a time. I am here for you, but I don't want to just miss this week. Okay, so we'll think about that. Message me if you need to work out something special, and we will have a chat. All right, I want to talk to you about butter sculptures. Said no math teacher ever, except me. Butter sculptures, as you know, are usually carved out of, they're big mountains of butter, right, that are carved. They're often kept in like a freezer or a walk-in at a restaurant or a hotel or something until a banquet to keep them cold, right, because as soon as they get warm, they start to melt. And we have butter sculptures today, and this is how they've been made. They're much bigger than this pencil, but they're the shape that you would get if you take a line and a point and then you rotate the line while keeping it fixed at that point, kind of like what I'm doing. It's sort of like an hourglass, okay? That shape, the relationship between a point and a line, is the basis for much of the geometry-related math that we do. Isn't that weird? We may have talked about these before, but it might have been with the older girls. It all blurs together. All right, so there's a rough diagram of what this shape looks like, right? I'm holding it in the middle and I'm rotating my pencil. That's the shape that it makes. Now, we have a bunch of these shapes. They're 3-dimensional, they're hollow in the middle, and they're quite tall. I would say they're probably close to 2 feet tall. And some nice assistant chef in a crisp white chef's jacket with a nice chef's hat on, is wheeling out a little cart of these for each of you. What we have are red hot butter knives, fresh out of the dishwasher. And what we're gonna do, each of us, are going to cut through these basic shapes, and what we're gonna find are some really interesting other shapes that in math we're going to be talking more and more about. So first we better make 4 of them, right? So I'm going to make mine a little bit smaller because you already know what they look like now. So draw with me. So you have 4 because we each have to cut our own. Okay, just imagine how satisfying this would really be if we could really do this in real life. Butter, cold, cold, cold butter, but we've got these scalding hot knives. And the first thing that we do is we just take our knife and cut right straight through that top part, all right? Now, when we take those two parts apart, if I can say that one more time, and look down into the face of it. If you imagine it as a graph, it would be a perfect circle, wouldn't it? Whether you're imagining the bottom of the top part or the top of the bottom part, it doesn't matter. If you want to take that off and look at it, or if you want to take it off and then take the other part and look at it, you're going to see a perfect circle. Huh, cool. Okay, thank you. That's called a circle. Now let's go to this one. And this time, instead of cutting it perfectly straight, let's cut it at an angle. Kind of like that. Okay? When we take that off and look at it, we're not going to have a perfect circle. Depending on the angle, it's going to be lopsided-ish because it's not perfectly flat. This is called an ellipse. In kindergarten, you learned this was called an oval, but we are upgrading to ellipse. That sounds way more cool, doesn't it? All right. Now let's do another one. Take your knife and chop down like that. Okay? Here we were still going underneath the top of it. This time we're cutting the top of it. Now, look at the side or look at the main object, but what you've got is a shape that looks something like this. Okay, there's a U shape, and that is called a parabola. And one more, this time cut so you go straight down and you get some of both. Now flip that open. You'll have to look at the main part for this one because the two, well, you could look at the two little chunks if you laid them out. It's going to be like that, right? There's going to be an open edge. This is called a hyperbola. A hyperbola. Okay, these are non-linear shapes. Linear, what's a linear one? What's a linear shape? Just a line. And we know a lot about those. Now, one thing we know about a line is that it has an equation. Y equals mx plus b. I've been beating that into you forever, haven't I? The Algebra 1/2ers just learned that today. I would squeeze it in here. If you've got room to write what I'm going to tell you next by the names and the pictures, go ahead and do it. But what I'm going to do is tell you that there's an equation, just like this is the standard equation for a line. There's one for a circle. It looks like this. That's just a random number I threw in there, but it's x squared plus y squared. What about an ellipse? The older girls learned how to graph ellipses this year and did a lot with that. That's not the way I like it, though. Oh, that's because that's how John's going to show it to you this time. Here's an example of the equation of an ellipse. Okay, here's an example of the equation of a parabola. And here is one that's an example of a hyperbola. So as you can see, there's lots of different shapes and sizes, but they involve squares quite often. They can have positive or negative numbers. We can rearrange them, but they basically have squares in them. That's the main thing about them that's different, right? Okay, keep that in mind. You don't need to memorize that or anything, but that's just kind of to give you a little bit of familiarity. Now, let's get to the algebra of this lesson because that's much more straightforward than all this weird butter sculpture cutting thing I've been talking about. What we're going to be working on is taking a system of equations and solving it. Well, duh, we've been doing that forever. But instead of it being two linear systems, we're going to mix it up. Okay, so this looks like pretty much like a linear equation, right? It's got a plane x and a plane, or a plane x and a plane y and some numbers. This looks more like a circle or something, right? We don't even need to know. But we can see that we have squares. That's the important thing to notice is that there's squares in this. Now, if there are squares, elimination won't work. because there's no way on God's green earth that we're going to multiply this to get squares. That is not going to happen if we can help it, right? If we're going to have to do that, we're going to do it as simple as possible. So what we're going to do is take this one, the linear one, we're going to solve for y. Whoops. Solve for y. That looks really messy. I'm going to add the y and subtract the 3. So it will be y equals 2x minus 3, right? And then we are going to square this much of it. Okay, so then we're going to say y squared equals, and then this will have to multiply 2x minus 3, 2x minus 3. We have to do the dance. The kids are in their studio. It's Saturday morning. The dust motes are flickering down through the sunshine. We start squaring. 4x squared minus 6x. Sit down, Penelope. Another 6x, and then plus 9. Okay, we squared the binomial that we got when we isolated, we solved it for y. Now we have a value for y squared. It's 4x squared minus 12x plus 9. Now we substitute that into a. This is a, this is b. Okay, solve equation b for y, right? So we rearranged this, we squared it, yikes, we squared that. Now we have a y squared value, and we're going to substitute that into this first one. So it's going to become x squared plus, now here comes the y squared, 4x squared minus 12x plus 9 equals 9. Okay, so that is all. We don't need parentheses around it. For algebra's sake, I just want you to see, yeah, that's the y squared value. Oh, Lord have mercy, right? So now we've got a great big hot mess here, and we're going to see what we can clean up. Let's try adding like terms, and let's bring the 9 over to this side. See what happens. Okay, so we have 5x squared minus 12x. Look, these just happen to cancel. Equals 0. How can we factor that? Well, we can't do it by inspection, because there's a 5 in front of it that we can't get rid of. We can't complete the square without a whole lot of drama. But you know what we can do? We can just factor out an x, right? We just pull an x out of both terms, and then we'll get 5x minus 12 equals 0. So we don't even need to factor it as a trinomial. We just factor it as a cute little, we just factor it as a binomial times an x. All right, that's not so bad, right? Now we know zero product theorem or zero factor theorem, both names make sense. Either x equals 0 or 5x minus 12 equals 0, right? Because we're multiplying them together. They equal 0. That means one or the other of them has to be 0. So these are our two possibilities. There's one answer. And then we just have to do a little algebra to sort this out. 5x equals positive 12. Oh. X equals 12 over 5. Those are our two values of x that we have found. But we haven't found any values for y yet. We've only found that there are two values for x. Spoilers, because there's a squared term in here, that 2 tells us that we're going to have two values for x. If it was third power, we would have 3 values for x. That's just a little tidbit. But now we need to solve for y. Okay, so I'm going to take these two values over here. Oh, I don't want to do that. Let me just keep working on this page. Okay, so now we've got x equals 0 as one possibility, and we've got x equals 12 over 5 as our other possibility. We have to find y values that connect with both of these. So we're going to pick one of these equations and we're going to plug in to get y. And we'll have to do a little algebra. I vote heavily for equation B. I don't want to solve squares. Thank you, no. It would work, but I don't want to. So we're going to use 2x minus y equals 3 as the method for solving. All right, I'm going to draw a little dividing line here so they don't intermingle. Okay, so now we're going to go 2 times 0 minus y equals 3. 2 times 0 is 0, so that means minus y equals 3. And then I can divide both sides by minus 1 if I like, and I get y equals minus 3. Does that sound reasonable to you? And now, if x equals 0, y equals 3, then our final answer is 0 minus 3. That's one solution to our original system of equations. The problem that will not die, right? It goes on and on. Okay, now we have to plug in here 2 times 12 over 5 minus y equals 3. All right, let's multiply. 24 over 5 minus y equals 3. All right, let's flip sides on those so we can get some clarity. So we'll subtract 3 and we'll add y to both sides. I'm not going to write it twice. It'll become 24 over 5 minus, now it's going to be minus 3, but I want to give it a denominator of 5. So I'm going to multiply it by 5 over 5 in my head. So it'll be 15 over 5 equals positive y. And now we're almost done. 24 minus 15 is 9 over 5 equals y. And so here's my second pair of points. If x is 12 over 5, then y is 9 over 5. And hallelujah, we did it. Those are a lot, aren't they? It's not necessarily difficult. We've done a lot of this before. There was nothing too horrible and scary. But that's a lot of calculating and blah, blah, blah. And it just gets annoying when you find, wait, I've got 2 answers. Oh, but no, they're both x's. I have to keep going to get 2 y's and then mush and compare. All right, that was the first problem of the 2 problems we need to do for this lesson. Shall we try another? Don't you wish we were carving up those butter sculptures still? That was easier than this. But this isn't too bad, right? Remember, these are called nonlinear equations because these original equations we're getting are not both lines. Now, this problem is unrelated to that whole nonlinear system thing. This is a problem that is going to be used for something called boat in a river problems. That always remind me of Lewis and Clark, so look forward to that. I love Lewis and Clark, P.S. Particularly William Clark. Okay. So this is not related to the nonlinear problems. There was one more thing I wanted to say about those, though. In the beginning, when John gives you the 2 equations, it's not important that you know which specific shape it is. It's important that you know, oh, that one doesn't have any squares, so it must be a line. This one has squares, so it must be one of those other butter shapes, okay? Later, John will start giving us more information, and we'll slowly build our knowledge. But right now, he's saying don't even worry about what shapes they are. Just know that one of them is not a line, all right? So don't worry about... Remember I gave you those equations as examples. Don't worry about like memorizing or trying to understand the differences. We'll get to that later. All right, so in these boat in a river problems, we're going to be using variables where B equals the boat, the speed of the boat, W equals the speed of the water, the current, And then we have time and distance downstream and time and distance upstream. So these are kind of like the rates, right? And then we have 2 times and we have 2 distances. Whoa, super crazy, right? And P.S. if you find the other kind of distance problems annoying, the Lord of the Rings and the Titanic and the Princess Bride style, these are different. You won't be so annoyed by these. So that's what's going on with the variables. We're just going to be handed 2 equations. You don't have to understand where these came from. We're just going to learn the mechanics of solving them. Okay. Now, we can see, let's eliminate, right? It's all set up. It's ready to go. And so we do. That's a D. It looks like a P. That goes away. Equals 40, right? But here's the problem. Oh, wait. This is 2. BTD, right? I didn't add them. Okay, and then we can divide by 2. And we can get this BTD thing equals 20. But this is 2 variables. It's not 1. And so it doesn't really give us an answer yet. That's the bad news. But the good news is we can still put this to good use, and we're close to solving. By going back to this, here's BTD. We could do it with either of these, but I like the one with the adding. Look, that's the same. So we can put 20 in right there, and then we'll be able to solve the rest of it. This is a great example of how we don't want to erase or hack things out too much. So I'm going to substitute 20, which equals BTD. I'm going to put it in right there. And so I'll get 20 plus 5TD equals 25. Yay! Now I can happily solve 5TD equals 5. Oh, that math is nice. So TD equals 1. Now let's see what John wants us to do. He wants us to solve the whole friggin' system. All right, well, that's fine. This is our first answer, and that is correct. These only have the D's. They don't have the U's. That's fine. But we need to find the B. I guess that's the only other thing we need, right? And we know BTD equals 20. So if T equals 1, then B times 1 equals 20. And so the speed of the boat must be 20. Yay. Okay, so the moral of the story here, and not everyone will be set up exactly like this, but the moral of the story is that if you find yourself with a 2-variable clump in your solution, that's okay. Just go back and look and see where you can put that information to work. Plug in and keep going. All right, we'll be doing more of these. I can't wait. Sacagawea will be there. We can debate how to say your name. It'll be great fun. All right, that's the end of lesson 85. Yay, so long, farewell.